Good morning, everyone. A very warm welcome to all the participants, dear faculty, and guests gathered here for day 6 of the QISKIT Fall Fest 2025, proudly being hosted by RGUKT Srikakulam, sponsored by IBM Quantum as a part of the global celebration of 100 years of quantum. I hope you all had a very refreshing start to the day because we have quite an exciting schedule for this entire day. So, before starting, let me walk you through the entire today's schedule. As you know, the 48-hour quantum hackathon that kicked off yesterday is full swing, and the energy, curiosity, creativity, and collaboration from all of your teams have been truly remarkable, guys. And to begin with today's proceedings, we are truly honored to host an in person guest lecture by Dr. Ritajit Majumdar, a research scientist at IBM Quantum, who is also going to be the hackathon jury panel member. And guess what, dear teams? This is going to be a real vault of knowledge and guidance you'll treasure for sure. And the session will take us deeper into the fascinating world of quantum technologies and their real world quantum career impacts. It's a perfect way to charge up our mornings with knowledge and curiosity. So, following the lecture, we'll be moving into the second review round of the Quantum Hackathon. A few quick announcements regarding the second review. The jury panel will be visiting each team to review your progress, and the judging criteria will be as follows. They will check the optimized circuit design and problem formulation, implementation plan, and innovative approach compared to existing methods you have chosen, coding progress, which means the complete pseudocode, and prepared documents like code notebooks, a clean documentation for the done and further procedures and plans, and the feasibility of the solution, which means how it is different and how it is working. You might need to show minimal execution and evidence of quantum learning also. So, this is how the judging criteria for the second review round of the quantum hackathon will be going on following this guest lecture. So, keep your momentum going, guys. You're right on your track for the day 6 of QISKIT Fall Fest 2025. And now to officially begin our day 6, I would like to invite our lead organizer, Mr. Katam Nikhil Teja, onto the dais to introduce and welcome our distinguished guest, Dr. Ritajit Majumdar. Let's give them a huge round of applause, everybody.
Good morning, everyone. So it's a pleasure to be here on the sixth day as well. So it gives me immense pleasure to introduce today's speaker. Dr. Ritajit Majumdar is a research scientist at IBM Quantum, based at the IBM India Research Lab. As part of the quantum algorithms and engineering team, he works with global academic collaborators to drive utility scale breakthroughs using IBM quantum technologies. He earned his Ph.D. from the Indian Statistical Institute and was a Fulbright-Nehru Doctoral Research Fellow at the IBM Thomas J. Watson Research Center in New York. A gold medalist from Calcutta University and recipient of the DST Inspire Fellowship. Dr. Majumdar has authored over 30 research papers and holds 13 patents. He has also contributed to academia as a faculty member at BP Podar Institute of Management and Technology and Calcutta University. He continues to inspire young minds through his remarkable journey and dedication to advancing quantum research and education. It is indeed a privilege to have him with us today to share his insights and experiences. On a personal note, sir, it's truly a huge moment for our team, myself, Kasim, and Praveen. We've always admired your work and will continue to follow your incredible contributions in the field. It's, it, it's honestly hard to believe that you are here with us today in our university. Join your hands and welcome Dr. Ritajit Majumdar sir onto the dais.
Okay. Uh, Thanks a lot to all the invitees who got me here. Really glad to be here. Really awesome what the institute is doing with this Kiskit Fall Fest. Definitely one of the biggest fall fests, and so many of you participants are joining. This is just awesome. I mean, this is the momentum that should come at this point. You know, I mean, this is the time with National Quantum Mission kicked off. IBM Quantum device coming to Amravati next year. This is the time, and I'm glad you are capturing this time because those who are not, they are missing out. And I'm glad you are just here capturing this. So, what I want to talk about today is one of the things what we expect to show quantum advantage. So let's think of what do we mean by quantum advantage? Why do we have quantum computers? Why do we need quantum computers? Let's ask this question. So if you say we have these classical computers that you all are sitting with, that I am standing here with, what more can we expect to gain from quantum computer? Well, I'm sure you all understand by now that we are not expecting a quantum computer to be something that will replace this classical computer. We are not going to play games on a quantum computer. We are not going to browse internet on a quantum computer. We are going to do some useful tasks. And these are the tasks which get so complicated. These are tasks which are of such complexity that even the best classical computer and the best classical supercomputers that we have today, they fail, right? So when you guys are starting now, say tomorrow some of you come up and say, I have designed a quantum sorting algorithm. My reaction will be, okay, good for you. What's the point? We have such good classical sorting algorithms. Quantum sorting algorithm, it's good for you. If you want to do, go ahead. That's not going to uh, break anything. That's not going to crack anything here. So we need a few domains where classical computer is struggling. That's where thinking of quantum computers, that's where going to quantum computer makes sense. And in general, there are four domains that we believe from IBM is going to be those things. I am not at all claiming that nothing outside these four domains can be interesting. Maybe quantum will not have an impact in anything outside these four domains. But these are the primary four domains where we can expect and we are seeing certain results already happening. First and foremost is chemistry and material science. And when I say chemistry and material science, that involves all biochemical stuffs and everything. So, drug discovery, designing better batteries, all of these things are going to be affected and they are already starting to get affected by a quantum computer. Second, optimization problem. And this we will go through in a lot of details today. Classical optimization problems, what they are, we will see some examples. Perhaps some of you already know. This is another field where we expect quantum is going to do a lot of improvement over what we have today. Third, high energy physics. That's a very complicated domain and it's very difficult to simulate classically. You all know perhaps about the CERN experiment, what they did, the Large Hadron Collider. What sort of experiment, what is the scale of experiment, what is the amount of money that goes into that experiment. So you can understand that a better simulation using a quantum computer, how useful that will be. And the fourth is you can think of finance sustainability. These are the four domains where we think quantum computer is going to be very useful. And that's how, as you go ahead in your careers, as you start learning quantum more, these are some of the domains where you should be thinking of going and making some contributions, learning these in more detail. And today we will look into combinatorial optimization. My request to you all will be, those of you who are listening to this live, online, whoever, just walk with me through the slides. Walk with me through the slides in such a way that if any of your friend is missing, even if you don't understand all the details, if any of your friend misses out this talk, you can explain that this is what he said in the slide. Perhaps I don't understand, but this is what he said. We will try to unravel a story here, understand the story. Don't try to go into too deep mathematics or anything inside this. Understand the story. Let's walk a journey together. So, one last thing before we get started. Maybe you have heard of certain algorithms. You know, whenever we talk of quantum computing, we start by saying Shor algorithm. It is going to break the crypto system and all of those things. When I was of your age, I used to go and tell, you know, all securities are broken. There is nothing called security. Everything is broken. But we see we are still secure, right? We are still using our ATM cards. We are still doing digital transaction. We are still secure. All our information is not hacked. So why is that happening? So what is happening with the promise of Shor algorithm? That is something what we call as a long-term algorithm. Short algorithm breaking the actual crypto system that we have today, it's going to take decades. Of course, that's a very, very interesting problem, but that's not something near term. Can we do something very useful today using a quantum computer? Yes, we can. And that is optimization is one of those. And we will go through a different type of formulation of algorithm than all these Shor, Grover, everything that we call as variational algorithms. So let's try to walk through what is variational algorithm, and as I requested, just walk through the slides with me. Let's try to unravel a story here together. So let's think of someone who is a very bad guest, and you have someone who is a very tolerant host. Okay. So we have a very tolerant host who wants to give a cup of coffee to the guest, and the guest is not happy with the coffee. And the guest is really bad, because if you go and give the coffee to the guest and you are asking, sir, is this good enough? The guest says, no, it can be better. So the natural question will be, sir, tell me, what do you want? You want more sugar? You want more milk, more coffee? Just tell me what I should do. And the answer the guest gives is, no, I am not going to tell you, but I don't like this coffee. So what can you do? You can do two things. First, you can say, bhar mein jaye. Coffee nahi pina, bhar mein jaye. You don't have to drink coffee anymore. Or if you are a very tolerant guest, you will try to say, okay, okay, sir, I'll try to make a coffee for you that you like. So now what can you do? Any thoughts? What can you do? I mean, the guest has just told you that he doesn't like the coffee, but the guest is so bad, he is not going to tell you what does he not like. Well, the only thing that you can do is you can say that, okay, I'll put in a bit more sugar, and then ask, sir, do you like it now? The guest says, no, 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 it's too sweet. So you understand, no, the guest doesn't like a lot of sugar. So you say, okay, the next step is I will prepare the coffee again. I will not add too much sugar. Maybe I'll put in a bit more coffee. Maybe the guest likes more coffee, likes it strong. Now the guest said, yes, I like this coffee, but it can still be better. So what we are doing here is something like a trial and error, right? Um, okay, yeah, I think this portion is not visible. Maybe we can. So what the best thing that you can do here is something like a trial and error. You add more sugar, you add less sugar, you add more coffee. Every time you take a feedback from the guest, ask whether the guest likes it or not. Accordingly, you either add the ingredient or you remove the ingredient, and you try this out for many, many times. At some point, the guest will either like it or he will say, okay, that's good enough. You don't have to try anymore. This is precisely, if you understand this, this is how variational algorithm works. You look into any particular problem, and we will walk through the combinatorial optimization of how do you find these things. But just to give you a broad overview, you start with a trial solution to your problem, because you don't know the solution. You start with a trial solution, and this solution is called an ansatz. The trial solution is called an ansatz. it has a few unknown variables. Just like in the coffee, we were saying that you can add more sugar, you can add more milk, you can add more coffee. All these are some variables that you can increase or decrease. You have a few variables, say m of them. Now, how do you get this guess? How do you get this trial solution, this answers, this thing? So what we will do is, this can either come from the domain knowledge, usually in chemistry and combinatorial optimization that we will walk through today. This comes from the domain knowledge. Or there can be domains where you don't know how to come up with the solution, you just come up with something heuristically. That's more or less machine learning, quantum machine learning for you. Now we calculate something called expectation value. We will again see, if you are not understanding, don't worry, we will again see what this is. Now we calculate something called expectation value. This is like taking feedback from the guest. uh, I, I, I have added these values for the parameters. Do you like the coffee now? Do you like it better than before? Do you like it worse than before? Can you give me some feedback? So this expectation value calculation is taking that feedback from the guest. And then you come up with a new set of parameters, just like we were doing that. Okay, you add a bit more milk, or you add less sugar. So you increase or decrease the values of these parameters, and you repeat this, and you hope that if you do this quite a few times, you will end up with a pretty good solution. Like, you can end up with a coffee that the guest finally likes. This is the variational algorithm approach that we use. As you can understand, it is very easy. It is really very easy algorithm. You just start with a guess, because you don't know. So if I start from guest house and I want to come here, and I don't know how to come here, I will walk in some direction, ask someone, is this the right direction? If not, I will take some other direction. If it is the right direction, I will follow that. It's exactly the same. So variational algorithm is exactly that approach that we do in day to day life. And what we will do today is to dive a bit more deeper into this variational approach for optimization problems. So whenever we want to solve a problem, any questions up to this on what is the philosophy of variational algorithms? Or was this clear? Okay. So whenever you are solving any problem, it need not be an optimization problem. Any problem, I would even say it need not be a quantum problem. You can apply this pattern for any problem that you are trying to solve. You should be taking 4 steps that we call QISKIT patterns. Let's talk of quantum problems here. The first thing is, see, we and a quantum computer don't speak the same language. The language that I understand is not the language that a quantum computer understands. So I cannot just go and tell a quantum computer that solve this optimization problem for me, solve this machine learning problem for me. A quantum computer doesn't understand that. So we need to map the problem of quantum circuit. I don't know if this is working. So we need to map the problem to quantum circuits and operators, whatever we are seeing, whatever we are talking of. Once we have done that, next step is, I have a circuit, I have a quantum circuit, which is something now a quantum computer understands. Now I need to optimize that for the hardware that I am going to run off. There are certain constraints to the hardware, and I need to optimize my circuit for the hardware. Third step, I run it on the hardware. What will happen when I run on the hardware? It will give me some zeros and ones. That is not the solution to my problem. Say I want to solve a chemistry problem. 0 and 1 is not the solution to the problem. From those 0 and 1, I need to come back to the problem that I am actually trying to solve. So that is the post-processing step. Given any problem, whenever you are working on quantum computing, take any problem, break it down into these 4 steps. It always makes easier, because you can understand that these four steps are independent of each other. When you are working on one step, you don't need to worry about the other. And you can actually go and think of doing research in any one of these steps. There is things to be done in all four of these steps. So say you are looking into a problem, you can say I will work on step 1. You can say no, my interest is I want to work on step 2. So there are things, there are research that is to be done on each and every step. Break things down. What we will look into today in more detail is step 1. I have been talking of this combinatorial optimization problem, and I told you that this language a quantum computer doesn't understand. So we need to make the quantum computer understand this language, and this is what we will see how it is done for an optimization problem. So let's come to what is a combinatorial optimization. It is something that we want to find out. We have a cost function c of x, and we want to find the values of x for which it is either maximized or minimized. Let's take an example. A very famous example is something called this knapsack. So what is knapsack? Say I have a bag, and there are so many things here. I want to steal some of the things from here, but I cannot start stealing everything because my bag only can fit something. So what should I steal so that I can steal some of the most valuable things from here? Maybe I would like to, I see a water bottle, I see a laptop lying next to each other. Which one should I take? Laptop, that's more valuable, right? If I want to steal, I should be stealing the laptop, not the water bottle. That is more valuable. So a knapsack problem is that given my bag has a particular capacity and I have many things sitting here and there, and each of them has a reward associated with it. So a laptop is more rewardful than a water bottle. How should I steal those things so that the reward is maximized, right? This is a classic knapsack problem. This is an example of combinatorial optimization. We have something called a, say, a vehicle routing problem. Say, I have a vehicle, I have some gas, it can run a few kilometers. I need to drop a few people. Which route should I take so that I can drop maximum people before having to refilling the gas again? These kind of problems, job scheduling problem. This is something very, very useful in industries. You have a set of machines. Think of this. You have a set of laptops. Right now, you guys are working on hackathon. Say you are a team, you have a set of laptops, you have certain parts of codes that you want to run. How should you run the job so that if all of the jobs are done, you want to just run the code as quickly as possible? You don't want to wait on a single laptop, or you have just said, okay, I will assign job 1 3 5, and I am taking forever to run job 1. Then 3 and 5 are just waiting. Some other team member is sitting idle. Just give him or her that job. So this is kind of job scheduling problem. All these problems are part of something that is called an combinatorial optimization. So it has mainly two things. First is what we call as X. X is the set of parameters that you want. You want need to assign some values to X. And Cx is the corresponding reward that you will get. That's a cost function. And you want to say maximize the reward. When I am stealing, I want to maximize the price of all the items that I have stole. Or you want to, in some cases, minimize the reward. If in a hackathon you want to minimize how long some of your team members is sitting idle and not doing anything, example. So uh, either you maximize or you minimize, right? And most of these problems are too difficult to solve directly. These are some of the classic NP hard problems. Most of these problems are NP hard, and therefore we often settle for something called an approximate solution. Like, it doesn't make sense to say, okay, how should you assign your jobs to your team members so that none of them sits idle for long? You take 3 days just to find this, and your hackathon is for 2 days. What's the point? So it's better to come up with an approximate solution, say in 30 minutes, that, okay, this is how the jobs will be assigned. Maybe that's not absolutely perfect, but that is good enough. So this good enough is important here because time is of importance. Your hackathon is for 2 days. You cannot just assign jobs for 3 days. So that's not going to work. You need some good enough solution. That's where we stick to And often these are some mathematical details we don't need to go into. How good that good enough is, there are some methods that's called an approximation ratio by which you can calculate how good is good enough. Let's look into this very particular classic problem that's called a max cut problem, right? So think of this problem as a graph. We have a graph. This is the example graph that I have here. And I have given you two colors, green and yellow. You can put any color to any vertex that you want, but you can only use green and yellow, nothing else. That's the constraint for you. Now, I will say that if you put a color, say, look into the age 0 and 1. Here, one of the colors is green, the other color is yellow. Such a case, I will say the age is cut. And look into 1 and 3. Both the vertices are yellow. I will say the age is not cut. Right? This is the definition of this. And you can assign the colors in any way that you want, but the goal I want to achieve is maximize the number of edges that are cut. This is the goal that I want to achieve. Any real world examples where this can be useful? Yes, right now we are all using our mobile phones here. Say I am using Vodafone. So say the tower, nearest tower of Vodafone here, it has some fault. It goes down. Should my phone immediately go down? No, it will take the connection from some other tower, right? Say that tower also goes down. It will take connection from third tower. How many towers should go down such that my phone will lose connection? Because there is no nearby tower from where you will get some connectivities. And you want this to be as high as possible. Say there are 10 towers from which my phone can take connection from. It is very unlikely all 10 towers will go down at the same time. That is very, very unlikely, right? So this is kind of a max cut problem, and you can understand this is very useful for telecommunication people to give a good service to their customers. And in terms of the language of mathematics or computer science, this is how we say that you have a graph, you color the vertices with green and yellow in such a way that the number of edges that you cut is maximized. The first and foremost thing that we do, we want to write it down as something called a cubo. So let's look into this and try to understand what is xu plus xv minus 2 xu xv. Let's look into a particular edge. Let's look into 0, 1. We know that from this assignment that I have selected, 0 and 1 are cut. So let's say xu is 1 if the color is green, it is 0 otherwise. So what happens to 0, 1? XU is 1 because this color is green. Just follow on. I mean, this is just coloring, right? XU is green, so this is 1. XV, this is yellow, so this is 0. Minus 2 XU XV, this is minus 1 into 0, which is 0. So this is the entire term gives me 1. On the other hand, if you look into 1 and 3, this is 1. XU is 1 because this is yellow. XV is 1 because this is yellow. This is 1 plus 1, 2, minus 2, 0. So what is this term really telling me? Whatever I just told you in terms of colors, this is capturing the same thing in terms of mathematics. If the edge is cut, then this is going to give you 1. This term is going to give you 1. If the edge is not cut, this term is going to give you 0. So what will happen when you sum over all the terms? Well, it will just tell you how many edges are cut. That's what we wanted. And now you want to assign xu, xv and everything in such a way that this summation is maximized. So whatever we just discussed in terms of colors, this is how we can write it down in terms of a mathematical symbol. This is something called a QUBO, quadratic unconstrained binary optimization. QUBO. Now, the first thing is a quantum computer doesn't understand zeros and ones. It understands plus one, minus one. Any of you can tell me why? You know, I think. Have you looked into eigenvalues and eigenvectors? Let's take, say, a Z matrix. What are the eigenvectors? 0 and 1. What are the eigenvalues? Plus 1, minus 1. Let's look into the X matrix. What are the eigenvectors? Plus and minus. What are the eigenvalues? Plus 1, minus 1. Always the eigenvalues are plus 1 and minus 1. So if you want something to be in the language of a quantum computer, you don't want it to be 0, 1. You want it to be plus 1, minus 1. Then there is a one-on-one correspondence between the eigenvalues of these matrices versus the assignment that you want to make. How do you do the change? Very simple. X equal to 1 minus z by 2. So z is plus 1 minus 1. When z is 1, when z is plus 1, x is 0. When z is minus 1, x is 1. Right? So it's a very simple way to go from plus 1, minus 1, 0, 1 back and forth. So now if you just do a very simple calculation, you can show that whatever we wrote here, what we called as cubo, if you take it to plus 1 minus 1, that is z, it becomes this term, 1 minus ZU ZV by 2. Now, what is my problem? How does my problem change? Well, the same problem. Now I have this cost function and I want to find an assignment such that the assignment is now no longer zeros and ones. The assignment is now plus 1 and minus 1 such that this cost function is maximized. Same as before. There is nothing changed. Once more, this small z plus 1 minus 1, this is not something a quantum computer understands. We just said why we are going to plus 1 minus 1, because those are the eigenvalues of quantum operators, right? So we need to go from this plus 1 minus 1 to operators whose eigenvalues will be plus 1 minus 1. Very simple. You have the Pauli Z matrix. So just replace small z with capital Z. You are done. Now this is the cost function that we want to solve for. This is the language that a quantum computer understands. So what happened? We started from saying that you want to color the vertices and we went down to something that you want to maximize this. This is a language that a quantum computer understands. You know Z are operators. These are Pauli operators. They have plus 1, minus 1 eigenvalues. So this is the language that a quantum computer now understands. Awesome. Great. This is something that is called a Hamiltonian. Previously, we had cubo. This is something, once you take the x term to the z term, this is called a Hamiltonian. Because we want to find eigenvalues and Hamiltonians are operators whose eigenvalues gives you the energies. How do we solve it? So first question to you all. I started by saying that we want to solve problems which are difficult for classical computers. We established that these are some NP hard problems, so known to be difficult problems for classical computers. We said this is a language that a quantum computer doesn't understand. We need to convert it into a language that a quantum computer will understand. And then we did some tricks here and there, and we ended up with a Hamiltonian. So now is it solved? Is it, can I solve it in a very simple way? Anyone thinks yes? Everyone thinks no? If you think no, that is correct. See, what have I done? I have just used two slides to take from one language to another language. What I would have done is something that a Google translator does, right? Nothing more. If this makes an NP hard problem into an easy problem, then you just show P is equal to NP. We can just all go from here to get the Turing Award, right? So we have not solved this problem. We have not made this problem easier. We have just taken it into a language that a quantum computer understands. Now let's try to solve this problem using a quantum computer. The approach that it takes is very, very simple. What will you do? Say you go to a class and your teacher shows you a problem, say a mathematics problem, which seems very hard to you. What will you do? You go to the teacher and say that, no, I cannot understand this. And the teacher will most likely say, start with an easier problem. You start solving that easier problem and slowly start building yourself up, and you will be able to solve the harder problem. Right? This is the approach that we all take. Start with an easier problem. Let's slowly build ourselves up that we can solve the harder problem. This is the approach that the quantum computer will also take. So this is the Hamiltonian. We call it problem Hamiltonian, HP. This is the problem that we want to solve. And we have already said this is a very hard problem to solve. So I cannot just immediately solve it using a quantum computer. Let's start with an easier problem. Let's just start with an easier problem. I am just calling it HM. This is a problem. This is a Hamiltonian whose eigenvalues we can very easily find. And that has nothing to do with HP. That's fine. But just like we said that the approach we will take, oh, this maths is very hard, let's try with a simpler mathematic problem. This is what we will say. This Hamiltonian is very hard to calculate eigenvalues. Let's start with a simpler Hamiltonian. Now, what we will do is we will slowly evolve ourselves from this easy Hamiltonian to the difficult Hamiltonian. You can see this is the approach we take every day in classes. You start by solving some easy problems, you move up, and you slowly build yourself up to more difficult problems. This is what we do. Start with the easy Hamiltonian, slowly evolve towards the more difficult Hamiltonian. And there is a guarantee that if you do this slowly, that is, if you try a lot of maths, you will get really good at the maths. So if you do this very slowly, then you will, if you start from here, you will definitely reach the solution of HP. Now, there is also one more thing. Say you cannot give, so let's suppose you are studying a particular chapter of mathematics. You cannot say that I'll keep doing sums and keep doing sums. You need to move on also, right? You cannot solve thousands and thousands of sum from a particular chapter. You need to move on. So similarly, you cannot be too slow. So if you are being not too slow, what will happen? You will end up not exactly in the solution of HP, very close to the solution of HP. That is guaranteed. And remember what we started by saying, these are hard problems. We will be happy with good enough solutions. So that's what we are doing here. We'll be very happy if you take it in a acceptable pace, but you reach close enough to the actual solution that I am interested in. Let's not aim for the perfect solution. Let's aim for a good enough solution. Right? The second question that you should be thinking, if you are not already thinking, you should be thinking that whatever you told me, you told us right now, has nothing to do with what we learned about quantum computing. We learned about qubits, we learned about quantum gates, we learned about measurement, and here is something that you are saying that start with a Hamiltonian, slowly evolve to another Hamiltonian. I mean, which one is the quantum computing that you are talking of? Where are the gates? Where are the qubits? You have not said anything about all of those. True. So this is something called a different form of computing called adiabatic computing. What we can do here is we can actually come down to what you all know, qubits, quantum gates, and everything from what we just learned. And you know what is this? What this is very simple. Say, I am talking right now. This is an analog signal. I guess most of you will know. This is an analog signal, whereas this mic, this is a device, this understands digital signal. So in between, there is a converter that goes from analog to digital, right? Most of you know this, I hope. There is something that goes from analog to digital. How do you go from analog to digital? In general, analog is a continuous thing. Digital is discrete. You cannot have a continuous thing in this mic. It is discrete. So what do? You sample at multiple points, right? You sample at multiple points, you take those values. Now, if you sample it at a very wide length, then it's not going to work. If you sample it pretty close, then you are going to get a sufficient good representation of my analog signal. And this is what the mic is doing. It is sampling my signal, it is breaking it down into discrete parts, but it is doing it in such a close manner that whenever you hear, it doesn't seem like something is breaking or something is cracking. It seems like whatever I am saying, it is exactly giving that to you. That is what we will do here right now. So you see this is a continuous path from HM to HP. We need to break it down into discrete paths. How will we do that? We will do that using quantum gates. So now comes the quantum computing, you understand. We will do that using quantum gates that we can think of. And okay. So some error in analog to digital conversion. So anyway, uh, so you see, we have these gates now, UHP gamma, UHP beta. How can you think of this? Think of this that you are trying to break a continuous path into discrete paths. And this gamma and beta are telling you the length of these paths, right? So the immediate question, how do I know the length? How do I know the length? You have just given a picture here. You have given a picture so that it seems it is very good. How do I know what is the length? We don't. Now let's connect back to that coffee making. I am here with parameters gamma and beta whose good values I don't know. So what can I do? Let's guess. Let's guess and try to improve ourselves, right? So we will start with some random values of gamma beta. We will see what is the cut size now we have. We will change the values of gamma and beta, and we will keep on doing this many times to get improved results. So there are some mathematical things here. Of course, you understand you can increase how many times you sample. The more you sample, the better it is. The more faithful is the representation. But the more you sample, the more number of unknown parameters you have. So previously you just had two parameters. Uh, Previously you just had two parameters. Now you see in this picture you have four parameters. These are denoted by P. In general, in the literature of QAOA, these are denoted by P, and you have four parameters. If you take P equal to 3, you will have six parameters. The more you break, the higher the value of P, the better is the solution. But the higher the value of P, more is the number of unknown parameters, which means you will have to do more trial and error. You will need more time. So there is always a trade-off between these two. So if we just try to write down what we just understood about QAOA, then what are the steps that we did? First, I need to start with some initial random parameters. I don't know what are good parameters. I need to start with some initial random parameters. Do you need a quantum computer to do that? No, just call numpy.randint or something. So a classical computer is good enough for that. You don't need a quantum computer for that. This step is classical. There is nothing quantum about this. Step 2, start with the initial ground state of this easy Hamiltonian HM. Can a classical computer do that? No. It is a Hamiltonian. You want to prepare its eigenstate. You need a quantum computer for that. So this is a quantum step. Next, you apply these operators, HP, gamma, HM, beta, P many times. You decide what your value of P will be. P equal to 1, only 2. P equal to 2, 4. You decide what your value of P will be. How will you apply these? These are quantum gates. You need a quantum computer for that. You prepare the qubits. You need a quantum computer for that. And therefore, this step is also quantum. Now, what you do is you have your parameters. You check what is the size of the cut. This is like taking the feedback. I have given some values to the parameter. Are these values good enough? This is like taking the feedback from them. How can you take the feedback? Well, that is classical. You just assign some values, look into the graph, and see how many edges have been cut. That's classical. There is nothing quantum about it. Finally, you come up with a new set of parameters, call them gamma nu and beta nu, and you repeat this again and again. And you expect that you will be able to improve the parameters in such a way that you will start getting better and better cut size. That's the entire QAOA algorithm. If you think, some of the steps here are classical, some of the steps here are quantum. So that's why it's called a hybrid quantum classical algorithm. Some of the most widely used algorithms in near term quantum computing. Here we talked of HP, HM. This came from a graph problem. If you replace this HP coming from a chemistry problem, use some UCCSD, Hartree-Fock methods or something that will be from a chemistry problem, the same recipe will solve a chemistry problem for you. If you replace this if by encoding some data, some image data, whatever data, cat, dog classification, whatever data, the same recipe will solve machine learning problems for you. All of them have the entire same recipe that we have here. You start with some initial random parameters, you prepare the ground state, and you prepare the problem Hamiltonian. How you prepare the problem Hamiltonian, that will depend from problem to problem. If it is an optimization problem, it is prepared in the way we discussed. If it is a chemistry problem, you need chemistry knowledge to do that. If it is a machine learning problem, you need to understand how to encode data to do that. But eventually, that is what is done. Now you calculate this in terms of optimization. This is telling me the number of cuts. If this is the chemistry problem, this will perhaps tell you the energy of the molecule. If this is a machine learning problem, maybe this will tell you the accuracy of the problem, F1 score of the problem. But it's the same thing, that just the values that we measure, it changes from problem to problem. And we keep on looping this few times to actually get a good set of parameters, a good set of results. So just like I am saying that here, I am expecting to maximize the number of cuts. If this were a machine learning problem, you would say that let's update the parameters so that my accuracy will be maximized. If this is a chemistry problem, you will say let's update the parameters so that my energy is minimized, whatever way. So the entire recipe that you see here works for optimization problem, works for chemistry problem, works for machine learning problems. And this is the hybrid quantum classical approach, the variational approach that we use. Why it's called variational? We are varying some of the parameters, and there is something called a variational principle. Let's not go into that. So any questions for up to this? If not, let's come to a very small thing, and I want to talk a different thing about this. What we talked about here, this is something very important, I would say, to understand. What we talked about in this, the cut problem, what I said, assign values, assign colors, green or yellow, on all the vertices, however way you like. Say you go and assign all the vertices as green. Is that a wrong solution? This is a very important question. We need to break this into these two steps and it becomes super clear. Is it a wrong solution? No. This is something very important to understand. It is not a wrong solution, it's a bad solution. Your cut size is 0. If all the vertices are assigned the color green or the color yellow, none of the edges are cut. It's a very bad assignment, but it's not an incorrect solution. There is no incorrect solution when you come to some this max cut problem. There is good solution, there is bad solution. There is no incorrect solution. So this is what we call as unconstrained optimization. There is no constraint to it. There is nothing that will tell you this is a correct solution, this is an incorrect solution. You only have good and bad. But you know, most of the problems are not like that. When you think of mathematics problem, there is always a correct answer and there are incorrect answers. And when you find the correct answer, maybe my method was better than yours. That can be. But whether the method is better than yours, that is a secondary question. The first question is, was the answer correct? If I come up with a very fancy method and my answer is incorrect, doesn't it doesn't mean anything. I come up with a very fancy answer, but very fancy method, but my answer is incorrect. It doesn't mean anything. So there is something that is called constrained optimization. Here you have this thing that this is a valid solution, this is an invalid solution. This is an important thing that you have here, something that we didn't have in MaxCut. Even if you put all the vertices as green, it is still a correct solution, it's just a bad solution. It's not an incorrect solution. So these type of problems, constraint optimization is also something that you can solve using a QAOA approach. The only change is previously we had that we want to do an assignment that maximizes this cost function. Now you will have a set of constraint assigned to it. What you can simply do, we won't go into details of this, don't worry. You can just take this constraint, add it as a penalty in your cost function. So the point is that I am not going to say your answer is correct or incorrect. If you give an incorrect answer, I will add a lot of penalty to you. So just to avoid the penalty, your algorithm will try to avoid those incorrect solutions. So it's kind of an indirect way of trying to tell the algorithm that go for the correct solution. Not a direct way, not a direct way of saying that you have to go to the correct solution. It's kind of saying that you have the liberty to go to the correct solution. If you go so, I will penalize you a lot. So the algorithm will try to avoid those things. And we can use QAOA for this constraint optimization as well. The moment you write down the cost function like this, we have already seen the recipe. This is a cubo, replace the x with z, replace small z with capital Z, and you are in for the algorithm. Done. So coming up with this cubo is definitely a research problem. Many of these studies have been done. You can go and look into some of those. You can come up with your own cubos for problems that has not been solved. One more thing that is a very useful area of research. I started by saying that you create some initial random parameters. Can you do something better than random parameters? Say I am trying to come to this place. I know this is within RGUKT. I should not be searching somewhere else outside the campus. I should be searching within the campus. I don't know where this is, but it's definitely inside this campus. So if I am searching outside the campus, that is total rubbish. There are many machine learning approaches people take that can you start with a good set of initial parameters instead of starting with some random parameters so that the number of times you have to repeat this can be reduced. So you see a lot of research still goes on here, lot of scopes to work on this. Let's not go into details of this. These are how you create circuits, but you can look into this. What I want to talk about is this one. So if you have seen this before, this is the roadmap of IBM Quantum up P33. Why am I showing you this? This roadmap gives you a very good idea of where you can contribute depending on your background. You may have a physics background, you may have a mathematics background, computer science background, statistics, chemistry, whatever. There is scope for everyone to come and contribute to this. Quantum computing is not a physics, it's not a domain that is only for physicists. And this map gives you exactly that. So I don't know how it is, but I will kind of walk you through this. Okay, this is very slow, but let's look into this lowest part. This lowest part, this is where the hardware is prepared. Of course, if you want to go and prepare hardware, you need to be an experimental physicist. There is nothing else is accepted. You have to be an experimental physicist. We work with superconducting qubits. You have to be experts in superconductors. If others work with ion traps or NMRs, you have to be experts in those. Only then you can go and contribute to this layer of computing, of the quantum computing stack. I am assuming most of you here are not experimental physicists. Great. Let's go a step up. You see, I told you all these algorithms and everything. I don't understand superconducting qubits. So, do I not work on a quantum computer? I do. Who takes care of the codes? Right now, you are writing codes. Do you know how things are done at the end? Do you know how pulses are generated? You don't. You don't have to. That's the point. You don't have to. So, this is the layer where Qiskit runtime sits. This is the layer where you can help a user who doesn't understand these pulse creations and everything, who is writing these Python codes, to come and take their codes, map it down into the pulses. A user doesn't need to understand. So if any of you here are interested in those compiler levels, this is the level where you have a lot of scope to work. This is the compilation level of quantum computing, if you think. And you see Qiskit runtime sits here. Okay, let's come to the top of that. Do I need to, I mean, if that is the only thing, that's still very critical. You still need to understand how pulses work and everything, how they are scheduled, all of those things. Not something everyone understands, not something everybody wants to understand. Great. Come, right now, if you go and submit a job, all of you who are sitting here, you can submit a job in the IBM Quantum system. Others who are doing hackathons right now outside this campus, they are submitting jobs. The system can only run a single job at a time. How do I schedule the jobs? You see, this is not a quantum question. This is a pure classical question you hear in OS and everything. How do you schedule the jobs? Remember, there is something different about this. You have all those preemptive methods in classical. You can stop a job and you can put other jobs, hold it for some time, then let it run. You cannot do that for a quantum computer. You cannot stop it in the middle, capture the entire state, start later. So this kind of scheduling is different when it comes to a computer than when it comes to a classical computer. Right now, what I didn't talk about, a lot of efforts on goes. I started by saying that we want to do problems which are intractable for classical computers, which are intractable for supercomputers. That's where quantum computing comes in. Let's say you have an entire workflow. Your workflow consists of multiple things. There are some of the things classical computers do very well. Some of the things the HPCs do very well. Some of the things quantum computers do very well. We don't need to compute and compete with each other and say, no, no, quantum is good, no, no, HPC is good, no, no, classical is sufficient. This is total rubbish. The entire workflow, whatever part is good enough for this classical computer, let it work on a classical computer. If there are portions where HPC works very well, let it work on HPC. There are always portions which requires quantum help. Go to quantum computer. So when I talk of scheduling, when I talk of orchestration, it is not only on a quantum computer. It is in an extended grid. That is where the state of the art is. It is in an extended grid where you have quantum computers sitting, classical computers sitting, supercomputers sitting. Each of them has their own bandwidth, each of them has their own workload. You want to orchestrate the job in such a way that all the works are done, none of the things are sitting idle. At the same time, the users don't have to wait for a long time. One very, very important requirement today we have flow orchestrations, all these things sitting here. As I said, HPC and quantum computer needs to work in hand with hand. They need to go together. The language that a quantum computer speaks, or the language that QISKIT speaks, right now you are all using QISKIT, which is based on Python. The language that HPC speaks is very different. They mostly use C type of thing because that's way faster. They use C. So you will see AI plugins for HPC. So how do you make these two different languages talk to each other? Again, very important, because if they don't talk with each other, then you cannot make them work together. Again, very important. Okay. On top of that, you have applications. So we can have a quantum computer, we can have a supercomputer, but if you don't know what to run on it, what's the point? So coming up with newer applications, improving those applications more and more. Optimization is one of the applications that we saw today. You have heard of other applications, I know. Coming up with newer applications of quantum computing, coming up with packages of that. This is something I want to, in the next slide, I want to give you a challenge kind of thing over a year, maybe. So let's think of this. Okay, let's come to the packaging thing after that. The final thing is data science, machine learning. You all heard of transpilation from Janani, right? You know what has happened recently? Transpilation, it means you take your quantum circuit, you map it to the physical hardware. It's a very, very hard problem. It's again an NP hard problem. People have spent years studying graph theory for that. And a team in IBM suddenly said that let's try reinforcement learning. State of the art. It is now the state of the art. The result that reinforcement learning gives beats any graph theoretic approach that we have today. We are even turning out by saying that, you know, you can have any unitary operator as your quantum gate. How do you break it down into basis gate sets? Recently there has been a paper from IBM where they are using reinforcement learning to do that. Lot of AI goes into quantum computing. Let's think that you are an expert in some of these domains. Let's say you are an expert in physics or in computer science. You want to do all these. So whatever we just saw today, um, all this Hamiltonian creation and everything, this you all do. But perhaps you don't want to learn too much about writing the codes. You don't want to know how to optimize, because everyone cannot learn everything. That's not possible. Everyone cannot learn everything. So there is this kind of QISKIT code assistant that we have now, that if you tell it the problem that you want to solve, it will generate the code for you. Faster thing. We are always using copilots and other kinds of thing. Why not for quantum? All those areas are there, and data science is super, super useful in making things more accessible, making things more faster, making things more useful. So if you are interested in machine learning, right now within IBM, we have quantum for AI, that's quantum machine learning. We have AI for quantum. All the examples that I gave you, you have places to work there. I want to leave you with a particular challenge. Those of you who are interested, you know, the way the ecosystem is evolving at this point, if you when you are going for a job application, when you are going for internship applications, if you come up and say that I know Grover's algorithm, I know Shor algorithm, I know variational algorithm, this is not going to crack the job for you. Everybody knows this. Think even in this single fall fest, there are tens of thousands, I think 15 or 17,000 attendees who are attending. Every one of them knows that. How do you stand out? You need to stand out from there. One of the biggest issue that we have today, um, the director of quantum in IBM, Jay Gambetta, he even gave a keynote talk in IEEE Quantum Week this year on this, that quantum devices are already pretty advanced. We have a very good roadmap towards fault tolerance. We need to make our softwares equally proficient. If it is not, say I say, you know, a quantum computer will do stuffs in nanoseconds, but you will need 1 hour to feed things within the quantum computer. What's the point? You need your classical software to be as proficient as a quantum computer. And this is where the ecosystem, not only IBM, I can vouch for IBM, other than IBM, they are also evolving. You need to have that sort of open source contributions, that development mentality. Whatever you do, whatever you study, you can be interested in applications, in any applications. Don't just stop by saying that I know the equations. Don't stop where I stopped today. I told you some equations and everything because we didn't have the scope for hands on here. That would have been very difficult. Don't stop there. Go ahead and do the hands on, write the codes. And when you write the code, once more, everyone is writing the code. Don't stop there. So this is a challenge I want to give to you. Maybe by next year, when all of you are a year older, you have learned more quantum computing. Since I talked of combinatorial optimization, I am just focusing on this, but you will immediately understand this is not something that needs to be restricted to optimization problems only. I only talked of max cut problem, but I also said there are other types of problems which are constrained. There are many many combinatorial optimization problems like the vehicle routing, knapsack, all of those I started off with today. Can you build a software around this? And you will immediately understand how useful this will be for you. Make a team, like you have a hackathon team right now. Make a team. Can you build a software? You take K problems. Say you take 5 problems to begin with. Take those 5 problems, whatever I showed today. So if I am an user, all I will give you is I want to solve problem number 2. Here is the graph. Solve it for me. Your software, your code should be able to create the Hamiltonian, able to create the cubo, create the Hamiltonian, create the circuit, run the variational, do the transpilation that Janani taught you, run the variational algorithm that we learned today, do the post processing, return it to the user. See, if you are doing this, why am I emphasizing in such a thing? Am I saying that take this as a 1 year challenge? Say you want to put in 5 of those. When can you put in 5 of those? I mean, don't just go to ChatGPT and say write the code to me. Then nothing works. When can you write code for 5 problems? When you know those 5 problems. When can you automate all the steps of those 5 problems? When you understand each and every step of those 5 problems, right? And this becomes a very good software for beginners to start with. And you know, all these parts, I have this construct circuit here particularly. Major part of my PhD was to do how you can optimize some of the circuits in max cut problem of QAOA that we discussed today. So if you have different types of problems, the circuit construction, the optimization of the circuit specific optimization, they will be different. You have research scopes here. I have done for max cut. You can do for vehicle routing. It can be a different type of circuit optimization. You have research scope here. You can show to people that you know combinatorial optimization, you know these 5 problems, you know all the steps, you have done problem specific studies, maybe you have done some sort of research on top of that, you understand transpilation, and you know variational algorithm. Everything what I just showed here today, a software like this, it shows to the recruiter you understand all of these things, right? It gives you visibility, if it gives you resources. And I don't know if CDAC will be interested, but I guess they will be. You learned about Quniverse. It's an abstraction, it's a layer over the IBM platform. Why not have another layer on, say, optimization on top of Quniverse? If you can make this happen, when you think that okay, optimization, this software looks good enough, why not reach out to CDAC? That, see, this is what we built, I want to put it on Quniverse, tell me what more do I need to do. They can help you out. Do the same for chemistry, do the same for machine learning, whatever you are interested in, just do. Don't just stop there. It's the development that you should be focusing on. And this is what we have been telling from IBM a lot, this one line: don't just do, develop. Whatever you are doing, you see this just single thing that I showed you here, if you can go and develop this, it shows you understand algorithm, you understand software writing, you understand all of these things. And if you can take it and put it on Quniverse, you understand open source contribution, you understand what it takes to write industry level codes. So That's the challenge I would like to put it on you, and I hope in 1 year I'll be able to see someone or at least a few of you taking up optimization, machine learning, whatever you are interested in. Do something like this and reach out to your mentors. If necessary, reach out to us. There will be more scopes on the way. So thank you. I'll stop here.
That was really such a mesmerizing session. I must talk about this session because from all the guest lectures we have had all over all this fest long, I felt this is the best one I've ever witnessed. All are the best guest lectures, but this one was really awesome. So Dr. Ritajit Majumdar sir took us on a really fascinating journey of into the world of combinatorial optimization through quantum computing, turning even the most complex ideas into beautifully understandable concepts. From sharing his little personal experiences that made us laugh a bit to the unforgettable quest to brew the perfect coffee analogy for explaining the variational algorithms, every moment of this session was a masterclass in clarity and curiosity. I must admit it. We also explored the QISKIT workflow step by step, mapping problems to circuits, optimizing for the hardware, executing on quantum systems, and also the post processing the results. It shows us how any quantum problem becomes approachable when viewed through these four structured steps. And Sir also beautifully connected theory to practice with examples like the knapsack, vehicle routing, the job scheduling problems, and showed us the max cut problem can be expressed as a cubo, a quadratic unconstrained binary operator, and further mapped into a Hamiltonian. And the way he blended depth with a little humor, even when battling with a cold and cough, was truly admirable. That's really great, sir. Despite not being in perfect health, he delivered one of the most engaging and insightful sessions we've ever had so far. And for that, we sincerely thank him from the bottom of our hearts. And sir, your explanation of quantum adiabatic algorithms, your reminder that we don't always need the perfect solution, we just need a good enough one, changes everything. And your clarity on the QAOA as a trotterization of QAA altogether made this session an unforgettable learning experience, sir. And what made this session even more special was a discussion of the IBM Quantum roadmap, outlining the quantum journey extending up to 2033 and beyond. The way you showed how each of us, even all of us, the beginners, can find our place and contribute based on our own backgrounds and strength was truly empowering for all of us. And on the top of it all, his guidance on the quantum career trajectory was an absolute bliss for beginners, enthusiasts, and the ones who are going to explore the quantum field like us, helping us see the bigger picture and the endless possibilities that lie ahead. Thank you so much to Dr. Ritajit Majumdar sir for sharing such valuable insights and for inspiring us with your brilliance, warmth, and dedication. You have truly been a treasure to our QISKIT Fall Fest 2025, sir. Thank you so much. And now, as we move ahead, I'd like to give you all a quick reminder about the hackathon participants and all. We'll soon be proceeding with the second review round, so please stay prepared with all your progress for the jury. So there is an unexpected news also. We all know that yesterday we have had the privilege of attending a truly enlightening and engaging session by Mr. Tilok Sadhukan sir on quantum computing engineer and quantum algorithm developer at CDAC Bangalore. We all know that was such an insightful session, and his session on QUniverse was truly a hands on understanding and experience that opened new dimensions of understanding the fascinating world of quantum computing. And Sir's clarity of thought and the way he connected complex concepts with practical insights made the session a highly impactful one for all of us. And we are deeply grateful for Mr. Tilok sir for taking the time to be with us and for sharing his valuable knowledge and experience. We actually tried for our sir to stay as safe till the end of the fest and be and grace us with his presence for the hackathon jury member also, but unfortunately that was impossible. Of course, that was a sad news. We will definitely miss you, sir. And so, as a token of our respect, gratitude, and admiration, we would like to offer a little felicitation, sir, for your remarkable contribution to all of us and your valuable insights. I'd like to request you to come on to the dais, please, sir. I kindly request our honorable dignitaries to do the honors of felicitating Mr. Tilok Sadhukan, sir. We also invite our director dignitaries to join us on the dais for this special moment of appreciation. I'd like to request all the student organizing team to come on to the dais. Let's get a little memory with us guests. The second review for the hackathon is going to start very soon. So, all dear participants, dear teams, get ready to present yourselves in the second review of the hackathon. Hope you all are ready with whatever the requirements I've mentioned earlier this session.